Electricity, as the best invention, has truly transformed our lives and provides us with conveniences and industrial development. However, fossil fuel, which is the main fuel source of electricity, is on the brink of running out. Many countries worldwide have set strict limits on the amounts of carbon dioxide emitted. How do we provide a highly efficient, environment-friendly, high-quality electricity power supply? The primary purpose of this study on superconducting power applications and accessories is to develop optimized products that lower net energy losses, further magnifying their efficiency advantage in optimized designs. Compared to conventional applications and accessories, the superconducting power applications innovatively reduce energy loss and lessen the amounts of carbon dioxide emitted. It also extends the life, improves asset utilization, as well as providing high-quality and eco-friendly power supply networks. Utilizing superconductor cables, there is a reduction of net electrical loss, which has a much lower electric resistance than copper and provides a cost savings to the power supplier. This enables an identical amount of electric power at lower voltages. Therefore, some substation and electric transformer installation expenses can be reduced. Additionally, the power transmission capacity of the superconducting cable system is 5 times higher than the existing copper-based cable systems. Replacing existing copper conducting cables into a superconductive cable system will not only enable efficient utilization of underground space in urban areas, but also solve the urban power supply shortage issues at the same time. A superconducting cable consists of mainly 5 parts. A copper former in the center is for short-circuit currents. Layers of superconducting tape are wound around the strands on the former, which forms an insulation core. Around the 3 cable cores flow liquid nitrogen for system cooling. The corrugated pipes and jacket are finally substantially surrounded. Superconducting cable systems commonly consist of cable, terminals, joint boxes, and a cooling system. The cooling system removes the heat generated during operating by forcing supercooling liquid nitrogen to circulate. A superconducting fault current limiter is a new type of power application which functions as a transient overcurrent suppressor when a fault occurs in a condensed power network. But there are negligible power losses during normal operating conditions when it is added. The superconducting fault current limiter is composed of an HTS module, high-speed switch, and a current limiting reactor. Under normal conditions, the power flows through the main path of the HTS module and the high-speed switch. When there is a fault in the power grid, a fault current passes through the HTS module. The fault current is far greater than the critical current of the superconductor. Therefore, the HTS module loses its zero resistance property and becomes resistive. The transition triggers the switch to cut off the main pass. This immediately forces the fault current to flow through the current limiting reactor that limits the current to a desired level. Since there is no current in the main path, the HTS module recovers its superconducting property shortly and gets ready for the next event. Therefore, the superconducting fault current limiter reduces the fault current of the power system immediately. The site for real grid installation and length of operation is decided to be at 154 kilovolts at the Ichon substation, considering the space, load condition, accessibility, etc. A superconducting cable system of 22.9 kilovolt, 50 megavolt ampere is installed between the number 5 main transformer and the 22.9 kilovolt line, which consists of an above-ground, duct, and offset section to mock actual site conditions. Power is supplied to the customer through a superconducting cable from the number 5 main transformer. The 22.9 kilovolt 630 ampere superconducting fault current limiter is installed after third-party inspection tests such as short circuit, impulse, voltage, etc. We have applied an environment-friendly solid insulated switchgear in order to successfully operate the HTS cable and superconducting fault current limiter in a real power grid for the first time in Korea. The substation automation system is also used for remote monitoring and control of both the HTS cable and superconducting fault current limiter. When it is installed, it's possible to keep the power supply stable by using a bypass path if they have any problems. Construction of the Echon substation's superconducting equipment was well managed based on the construction process system, which consists of construction of a cooling, control center, cable pulling, jointing, installation of cooling system, and commissioning a test. The monitor and control system for superconductor power equipment based on IEC 61850 substation automation was installed and connected to the SCADA system, which is monitoring and controlling the other conventional power applications in the real power grid. It's possible to promptly and stably operate in the case of an abnormal or urgent situation. Our superconductivity technology, considered a dream technology during the 20th century, will be a pioneer in the new world and blossom in the 21st century. As a successful cutting-edge new technology concept, it provides high-capacity transmission, prevents blackouts on a grand scale, and will upgrade and enhance existing cable system technology. We will mark an epoch in the electric industry and play a leading role in the green low-carbon environment energy industry.